everybody. My name's Sheila. I'm a planetary scientist and I'm the Education, Outreach and Diversity Officer at the Royal Astronomical Society. Thanks for joining us today. Today's topic is exoplanets and aliens and solar system formation. In 2 weeks' time, the session will be on the Wednesday, not the Tuesday. So do keep an eye out for that one when the Eventbrite link goes live. If you've missed any, you can catch up with recordings on YouTube. And if you have any requests for future topics, please email me or write them in the chat box and we will try and accommodate those requests. I've muted you all so it's not too noisy. And if you do want to ask me questions or say anything while I'm talking, then you can send me a message using the chat. And we've had a few shout outs, we've had a few birthdays, and some suggestions already for topics, which is fantastic. So you can keep doing that. And don't worry, I can't see your faces apart from about 4 different people. So those of you that don't want to be recorded have obviously switched your cameras off, which is excellent stuff. Okay, the first thing I'm going to do is share my screen with you because I have talked for long enough and I want to show you some slides. So those of you that have come on one of these sessions already will have heard me talk about careers and the space industry already. But if you haven't, then I would just like to have a couple of minutes before we talk about our topic today to tell you about what it's like being a planetary scientist and working in the space industry. If at any point anything goes wrong with the screen or the internet or anything like that, I'll try and reconnect straight away. If you can't see my slides, just drop me a message on the chat and I'll try and share the screen again. And we will have recordings of these sessions if for some reason we can't get back online almost immediately. Okay, so today we're going to be talking about planetary formation, exoplanets and aliens. So I've had a really cool life and career working in the space industry, and I'm really lucky that by studying physics and astrophysics and space, I've got to meet some really fantastic people. I've traveled all over the world. I've been part of missions, international space missions, and I've had a lot of fun. So I decided I wanted to be an astronaut or work in the space industry when I was about 13. I did science, I chose all my science GCSEs, and I did physics, maths, chemistry and Spanish at A-level. And then I studied physics and astrophysics at university, and I continued studying to do something called a PhD for another 3.5 to 4 years at the Mullard Space Science Laboratory, which is part of UCL. And during that time, I studied the planet Saturn using a spacecraft called the Cassini spacecraft, which was orbiting Saturn for about 14 years before it smashed into the atmosphere of Saturn. And now I work for the Royal Astronomical Society. And what the Royal Astronomical Society is what we call a learned society, representing astronomers, geophysicists, space scientists, planetary scientists, all over the globe, not just in the UK. When the lockdown is not in place, the office is in central London on Piccadilly in a building called Burlington House. And in there you can find some very cool meeting rooms and one of the biggest astronomy libraries in the UK. When all of this finishes, and if you're in London and our building is open, you can come and visit us, and we do all sorts of different things in the building, but we are also doing a lot obviously online at the moment. Now, the Royal Astronomical Society was founded in 1820, which means it's 200 years old this year, and our first president was William Herschel. There's a picture of him on the bottom left of this screen. And he was the guy that found or first discovered Uranus, or saw Uranus for the first time with his telescope. And one of our more recent previous presidents was the guy next to him in the blue shirt, Professor John Zarnecki, an amazing planetary scientist and a colleague of mine. But the reason I show these pictures is because common perceptions of astronomers are that they are old white men. But I would like astronomers for the future to be of all different shapes and sizes and come from different places. And in the next 200 years, hopefully, you guys will be some of the astronomers and geophysicists of the future. So there's lots of jobs in the space industry. It's not just about being an astronaut, although that would be a very cool job. I've not been into space yet, but I would like to. And most of my career decisions have been the way they have been so that I can eventually go up into space. But there are lots of other jobs. There's astrobiologists, so using biology to work out what aliens might look like or where they might live. You could be a scientist, you could be an engineer, you could be a teacher, you could be a planetary scientist like me, you could work using data from the bottom of the ocean or the Antarctic, you could do something called space weather risk management. And then there are more unusual jobs in the space industry, for example, space lawyer, space journalist, space TV presenter, space doctor. Basically, if you like space and you like other things as well, you could work in the space industry. If you're very, very good at art, you could be a space artist. There's literally any job that you are interested in, you could do that in the space industry, which is really cool. And a couple of questions so far. I haven't been into space. My favourite planet is Saturn because of studying it for 4 years for my PhD. And a cosmonaut is basically the Russian for astronaut. So cosmonauts and astronauts are the same thing, but cosmonaut is the Russian. So in the last lecture, we talked a lot about the life cycle of stars. And we talked about how the sun was formed or was probably formed. And today we're going to talk about the formation of our solar system and then look at planets outside of our solar system and the idea that there might be life outside of our solar system or maybe in our solar system. This picture shows you the planets in our solar system to scale, but not in terms of the size of the solar system. So they're not all in a line and they're not that close together. But from the left, we've got the sun, then Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And then there is Pluto there as well, although we now classify that as a dwarf planet. So when the sun was first formed, there was basically a big ball of gas, and gravity had a really important part to play in bringing the gas and the dust together. And eventually the gas and the gases were brought so close together under gravity that the pressure increased and the temperature increased, and then the gases were able to start burning, and the star, our sun in this case, was the star that was formed at the center of the solar system. And then there were lots of leftover materials which then were used to make the other objects in our solar system. It's all to do with gravity. It's all to do with gravity. Gravity is very important in pretty much everything in space. Even though it's a very small force, it's really, really important in why planets go around the sun, why the sun orbits around the center of our galaxy, why stars orbit in the way they do, why there are rings around Saturn. Gravity is really, really important. So when the solar system started forming, there were lots of leftover rocks and metals and ices, and they then started clumping together under gravity as well. Now, the closer ones were close enough to the sun that it was warmer, and the inner planets, Mercury, Venus, Earth, and Mars, were formed inside of something called the frost line. And then outside of the frost line, where you're further away from the sun, the gas planets, Jupiter, Saturn, Uranus, and Neptune, were able to form from leftover gases and ices at the edges of our solar system. Now, a couple of other questions. We'll talk about aliens at the end, so I'll answer that one at the end. Someone has asked, what's the difference between astrology and astronomy? Well, astronomy is the science, and we use technology and data to learn more about everything in space, stars and planets and black holes and all that kind of stuff, but real data, real science. Astrology is looking at the stars and the pattern of stars that they make, and imagining that that has some kind of influence on how we feel and how we act. So star signs, astrology is all to do with star signs, but it's not scientific, whereas astronomy is the science, scientific. Okay, so you have this big ball of cloud and dust and leftover remnants from when the sun was born, and they start coming together under gravity, which has been around since the beginning of our universe. Whenever anything has mass, it has gravity. So even us, we have mass, so we have a gravitational force, but planets and suns and galaxies and things have lots and lots and lots of matter in them, so their gravitational forces are a lot higher. So the sun is formed in the middle of the solar system and starts burning. And then there's lots of leftover material from the sun's formation, gases, dust, ices, and they clump together under gravity to start to form the planet in our solar system. The further out you go from the sun, the colder it gets. So the outer planets and the other objects in the solar system further out from that tend to have ices in them. So for example, comets at the edge of our solar system are basically massive, dirty snowballs full of ice. And these materials come together, and there are lots of small clumps of material, and then they clump together and clump together and clump together, just like making a snowball, till eventually you've got really big objects orbiting around the sun. And those are what makes our planets. So you've got these planetesimals, which are small, like baby planets. They collide with each other and stick together and make larger and larger and larger planets, until you are eventually forming solar systems just like ours. So you start with this big ball of gas and dust, and under gravity, they come together, and the leftover rocks form the inner planets, Mercury, Venus, Earth, and Mars, and the leftover gases and dust and ice form the outer gassy planets like Jupiter, Saturn, Uranus, and Neptune. And we can measure how long it took us, or it took the solar system to form. How do we know? How can we measure this? Well, the solar system formed about 4.5 billion years ago, around the same time as the sun formed, which makes sense because we think that the leftover materials from the sun's formation became the planets in the solar system. But how do we know? And there are various ways that we can measure this. So when the Apollo astronauts went to the moon, they took they dug up lunar samples or rocks from the moon and brought them back to Earth, and they had massive sacks of these moon rocks. And we can use something called carbon dating to date those rocks, and those rocks are about 4.5 billion years old. The other thing we can measure is meteorites. So those are rocks that have fallen through our atmosphere and landed on the surface of the Earth. They might be from asteroids, they might be from other places in the solar system. And if they land on the Earth, we can collect them and we can date them. And again, they come out at about 4.5 billion years old. And the Earth itself, we can take samples from the Earth and look at the rock within the Earth, and again it matches. It's about 4.5 billion years old. I have touched meteorites before from Mars, so Martian meteorites, and I have seen moon rocks, so some of these rocks that the Apollo astronauts brought back from the moon, but I haven't touched one with my bare hands, unfortunately. There's not that many of those rocks left, and so obviously the people in the space industry are quite protective over those rocks. And the other way we know that our solar system formed in that way and is that age is because we can look around at other solar systems that are forming. So if you look at the Orion constellation, which is the Hunter, there is something called the Orion Nebula, which is a big cloud of dust and gas in the constellation of Orion. And we know that planets can form in these situations, and we can take pictures of them. So what you can see in the left-hand picture is planetary formation around stars. These kind of areas of can't speak today, areas of gas and dust where planets will eventually form around stars, which means that we can also have a look for solar systems outside of our own, which we call extrasolar solar systems, and we can look for planets outside of our solar system, which are called extrasolar planets, or exoplanets for short. Now, there's lots of different ways to detect exoplanets, and people have been looking up at the sky for a long time, and technology has got better and better, but it's taken us a lot of time to see exoplanets. So we have only recently, since the 1990s, been seeing or being able to see planets outside of our solar system. And the reasons behind that is because it's actually quite hard. You need really good telescopes to be able to see or detect planets outside of our solar system. Now, there are lots of different methods to do this. The first one is called astrometry. So all the stars move slowly across the sky in a cycle, just like we move, and we orbit around the sun. And this motion is called proper motion. But sometimes stars do not follow proper motion. And in this little graphic, there is one star that does not follow proper motion. It has unusual proper motion. Can you see it? And can anyone type to me why they think that star might not have proper motion? So I'll just give you a second. I'll do that again. Can you see the star that doesn't follow proper motion? And are there any suggestions to why? Because the gravity of other stars are pulling it towards them because it's got an exoplanet. Is it orbiting something else? Good. There's some fantastic answers here. So what's going on here is that the star that's not following proper motion actually has, or probably has, a planet orbiting it, or an exoplanet orbiting it. And like I said, gravity has effects. No matter how big you are, if you have mass, you have a gravitational attraction. And the star has got a planet going around it, and that planet is exerting gravitational force on the star and vice versa, and that's causing the star to actually move with this wobble. And that is one way of detecting an exoplanet. And you can actually measure the speeds of these stars and things, and you can really work out what type of planet is going around the star and stuff. There's another method to look for a planet going around another star. You can't, or you might not be able to see the planet, but what you can do is measure how much light comes off that star over a period of time. So the bottom graph is going to show you the magnitude or the brightness of that star over a period of time. And what you might see is that it's at a certain level, and then it dips down, and then it comes back up again. And what we think is happening there, and what we can measure is happening there, is that a planet is actually orbiting around that star, and as it orbits in front of that star, it blocks out some of the light, and so the brightness of that star goes down by a little, by a very small amount. And so that's called transit photometry. And you can measure all sorts of things using that. You can see how big the planet is. You can work out how long it takes to orbit its star. And we orbit our star, our sun, once per year. So you can measure how long a year is on a different planet using this method. You can also work out its temperature. You can work out how fast it's moving. You can look at the atmosphere of that planet. So it's really interesting, actually. Transit photometry is very, very useful in looking for exoplanets. And so there's a question about orbiting. So in terms of stars and planets, we always have the star at the center of the solar system, and then the planets orbit around the star. It's never the other way because of the sizes and the formation process. So whenever we look at solar systems, whether it's our solar system or one outside of us, you always have a star like the sun, or bigger or smaller than the sun, with the planets orbiting around that. Another method, so we can see transits. We can see the transits of Venus or Mercury when they cross across the path of our sun. So from the point of view of the Earth, we see this happening with Mercury or Venus. You should never look at the sun with the naked eye or directly through a telescope. Make sure if you are doing any solar astronomy, you are using the correct filters on your telescopes or the correct equipment, because it can be very dangerous to look at the sun directly. But for example, you can see Mercury crossing across the path of the sun, and you can measure how long it takes, and you can learn more things about Mercury by looking at the transit across the path of the sun. So another method for looking for exoplanets or planets outside of our solar system is something called the Doppler method. So we've already talked about the fact that if there's a planet going around a star, it makes the star wobble a little bit because of the gravitational attraction or deflection. And this means that the star kind of wobbles on its path, and wobbles slightly, that it will either appear from the Earth to be moving towards us or away from us. And we can measure this wobble. If it's moving towards us, it looks like the light that it gives off is shifted towards the blue end of the spectrum. And if it is traveling away from us, it looks like the light is shifted towards the red end of the spectrum. And we can measure this, which is really useful, again, for looking for planets outside of our solar system. That's a slightly more difficult one. The transit one seems to be the most popular and the sort of easiest for us to understand. Now, they are good techniques. They are particularly good for finding large planets that orbit very fast and close to their star. And most of the exoplanets that have been found are what we call hot Jupiters, which means they are about the size of Jupiter, and they are very, very, very hot because they are very close to their star. So even though it's interesting to find those kinds of planets, it's not that good for looking for life like us, because we don't believe that aliens like us could live on a planet that was very close to its star, because it would be too hot. And these numbers are wrong now. So there are more than, I think, almost 5,000 exoplanets that have been found. Many of them have been found by a spacecraft called Kepler, which mostly uses the transit method to find exoplanets. By finding these planets, we can then look at how big they are, what temperature they are, what their atmosphere is like, what their surfaces are like. And there's a few hundred at least which we think are kind of rocky planets and orbit their sun at the right distance to be the right temperature, or when I say the right temperature, the most similar to the temperatures on Earth. So we're always looking for life like us. And when was this? This was March 2019. So the exoplanet tally by the Kepler spacecraft was set to pass 4,000. So quite a huge number of planets outside of our solar system. And they're all quite interesting. We don't have images of them. So when you see pictures of other planets, they tend to be kind of creatively drawn based on data. But we do know of solar systems outside of our own. So different size stars, so G-type stars are like our sun. And we've seen a G-type star with a planet around it that's probably about the same or slightly bigger than the Earth. And then there's different types of stars, and we keep spotting planets orbiting different types of stars at different distances. And if you're really interested in finding those exoplanets, you can do a science experiment using real data from these spacecraft at home. If you go to www.planethunters.org, you might be able to find a planet outside of our solar system. And it's a really nice and fun thing to do. And all you need is a computer and an internet connection, which is perfect for at the moment. What these extra solar systems look like, we can work out some of the stuff, but we can't really know unless we were able to get there, because the planets are so small that even telescopes on the Earth can't see them. We can see the stars, and we can use those methods that I talked about to work out where the planets are, but we can't see them with the naked eye or even with some telescopes because they are so far away. They're just so far away. But we have been able to spot exoplanets. And again, these are just graphical representations of what they could look like. We've got Earth here on the right-hand side. So generally, the planets that we find are bigger than Earth and different atmospheric conditions. So not ideal for looking for life like us, but still very interesting. What they look like on the surface, we definitely don't know. And again, this is just an artist's conception of what it could look like on the surface of a planet outside of our solar system. A bit like Star Wars or Star Trek or something like that, if you think. Now, because we're finding planets outside of our solar system, it makes you think about life on Earth and the possibility of life outside of our solar system. And so we've learned that the solar system formed about 4.5 billion years ago. And then over time, life evolved. First of all, there were single-celled organisms, then multi-celled organisms, then invertebrates and plants, and then dinosaurs, and then a version of people, until we end up with today, with people like us. Now, the one thing we have realized then is that it takes a long time, billions of years, for life to evolve. So when we're looking for planets, if we want them to have life on, we need to look for pretty old planets. So that's something to keep in mind. And when we do find an exoplanet, then how do we know that it could support life, and what does it need? So if you want to have a think about these, you can just have a chat if you're with someone, or you can write to me on the chat. What do we need for life to establish itself on Earth or on other planets? I'll just give you a second to have a think about that. So it was planethunters.org was the website for that searching. Nobody's ever gone to an exoplanet because they're so far away. They're so far away, we don't have the technology. And the YouTube channel where the recordings will be, if you search for Royal Astronomical Society on YouTube, then you will be able to see the recordings. So my question was, what does life need to establish itself? And some of your replies include oxygen, plants, food, the right temperatures, water, the right temperatures, liquid water, warmth, light, cold, shelter, food. Excellent stuff. Let's have a look. Right, so requirements for life. Again, we're talking about life like us. Time. So I mentioned time already. It took us billions of years to evolve. So if you find a new planet, it's probably unlikely that there will be life on it. Water. And we know we need liquid water, and Earth needs liquid water to provide for life like us. So we tend to look for liquid water when we're looking for life outside of our solar system. Energy, and that includes food. So we get our energy from the sun, and then plants, and we get our food from plants and animals. But that means that the planet going around the sun can't be too close or too far away from its star. It doesn't want too much energy or not enough energy. And then a source. So where did the first life forms come from? What caused those singular cells to then change into multiple cells, to change into invertebrates and plants and dinosaurs, etc., etc. So there's lots to think about in terms of requirements for life. And one of the things we can do as astronomers is look for the planets in the right conditions. And we call one of these conditions the Goldilocks zone. So just like Goldilocks, her porridge was too hot, and then it was too cold, and then it was just right. We look for planets in what we call the habitable zone. If they're too close to their star, it's too hot. If they're too far away from their star, it's too cold. But if they're right in the middle in the habitable zone, it's just right. And we don't want it too hot or too cold. We want it where liquid water might be able to occur. There are various different sections of the habitable zone. There are zones where microbes might live, and there's zones where liquid water might stay a liquid for a very long time. So Mars, for example, we think had liquid water on it in the past, but now all the water is frozen as ice. So it's not in this habitable zone anymore. And if you plot the mass of the star on the left and the distance from the star on the bottom, on the x-axis, on the top here we've got our sun, and then we've plotted the planets in our solar system, and you can see Venus, Earth and Mars just about fit in the habitable zone. And below that we've got a solar system called, well, the star is called Gliese 581, and that star is being orbited by at least 6 planets. So there is a solar system kind of like ours, but outside of our solar system, very, very far away. And there's G and D that fit inside that habitable zone. So maybe G and D would be the sorts of places where life like us could exist. And maybe we do have microbial life inside our own solar system. People used to think that there was evidence for sort of microbial life, bacteria type stuff on Mars, but we haven't found any proper evidence for that. And there are other places in the solar system where we think that life could potentially exist. So moons of Saturn and Jupiter, for example, Europa is covered in an ice crust. And we think that underneath the ice crust of Europa, one of Jupiter's moons, there's a salty water ocean. And maybe swimming about in that ocean, it could have microbial, not fish, but sort of single cell organisms or extremophiles, which are tiny bacteria that can live in extreme environments. Maybe Europa or Enceladus, which is a moon of Saturn, has life on it already. So if you follow a path into the space industry and you're interested in this sort of thing, please go to Europa or Enceladus and drill through the ice and swim about in those oceans and see if there is life within our solar system. But like I said, not intelligent life. It would have to be microbial life to survive in those types of conditions. And that kind of brings us on to the thought of, is there intelligent life in the galaxy or the universe, and how might we detect it? Well, there are various ideas. There's a search for extraterrestrial intelligence, and they put all kinds of experiments in place for over 20 years. So basically they send out radio signals into space, and they search for radio signals coming towards the Earth in the hope of actually detecting aliens. And so far there has been no degree of success at all, unfortunately. But that's not to say that there isn't intelligent life in the universe. It's just maybe we haven't found it yet, or maybe it's so intelligent it doesn't want to be found. So we'll have to see. And we can listen for signals too using big radio telescopes such as Jodrell Bank Observatory in Cheshire. And we have sent out signals into space. On the Voyager missions, there's a gold disc with different drawings on, which is supposed to represent human evolution and mankind. And the gold disc also had some recordings on, which was supposed to be sounds that you might hear on Earth, and these kind of very crude pictures of people and things like that. So maybe there are aliens out there that have received this gold disc and don't know what it actually means. But you know, who knows really, because the universe is so huge. We just honestly, we don't really know. And the fact that we are here is one of those kind of things that, is it coincidence, or because we're here, maybe there's another Earth somewhere with intelligent life on it as well. Sorry, just go do the next one. Okay, so one of the things humans have tried to do is to work out how many civilizations there are in our galaxy. And one of the ways was by creating this equation. So there's a scientist called Drake, and he's created this equation to measure the number of civilizations broadcasting across the galaxy. So n equals the number of civilizations broadcasting across the galaxy. And by plugging numbers into all these letters, you can work out the number of civilizations broadcasting across the galaxy. Now, these different letters represent different things. So R is the rate of star formation in the galaxy, which we can measure. F is the fraction of stars that have planets, and we are starting to be able to measure that now with these exoplanets. N is the number of Earth-like planets per system, and again, we can measure that to a certain extent. And then it goes a little bit wrong, because this FL is a fraction of habitable planets on which life evolves. At the moment, F equals 1, because the only habitable planet with life on that we know about is Earth. And then it gets a bit more loopy. So FI is the probability of intelligence developing, which we just don't know. FC is the probability that life will communicate. And again, we've been communicating into space for quite a long time now, but we've never heard anything or never had anyone communicate back with us. And then L is the planet's lifetime during which it supports a technological civilization in order to communicate. And if you think about humans and Earth, how long have we had a technological civilization? So the Drake equation is really interesting, but we don't really have enough evidence to plug all those numbers in to work out how many aliens there are in space trying to communicate with us. And the problem is, if we do find intelligent life, is this going to be a good thing for us? Will it bring us benefits, or might this involve dangers? And what would aliens look like? You know, will they be little green men or octopus, or would they look like human beings because they've evolved on Earth-like planets? So there's lots and lots of different things to think about. Now, just to finish the talk part of this session, I've got a little quiz, just 4 questions. And you can answer using the chat or with people that you're with at the moment. I'll give you 5 minutes to, or a couple of minutes to answer that quiz. So question number 1, what objects help us calculate the age of the solar system? Question number 2, most exoplanets are discovered when they pass in front of their star and dim its light. What's this process called? Question number 3, the place in a planetary system where liquid water can survive is called what? And question number 4, what is the name of the equation to estimate how many intelligent life forms there might be out there? So have a go at those. Okay, getting some good answers here on the chat. Excellent. So question number 1, what objects help us calculate the age of the solar system? So you could have had a couple of things. You could have had moon rocks, or you could have had meteorites, or also rocks from the Earth that we can also date. Question number 2, most exoplanets are discovered when they pass in front of their star and dim its light. And this process is called the transit method or transit photometry. So I talked about 3 different methods, and the transit one was the best. Well, not the best, but the most successful, I suppose. Okay, question number 3. what is the place in a planetary system where liquid water can survive cold? And the simplest answer is a habitable zone, but some of you have given me more specific, so the different types of habitable zone. You can have Goldilocks zone as well. And question number 4, what's the equation called to work out how many intelligent life forms there might be out there? And that is, of course, the Drake equation. Okay, so that is that's the end of my talk about the topic. I can answer more questions now, so if you have any more questions for me, please type them in the group chat. They don't have to be about this topic, they can be about any space topic. They can also be about my career and what I do. They can be any kind of questions that you might have about what you should study at school, or popular astronomy, or anything. And also don't forget, I would like suggestions for future topics. And in 2 weeks' time, this session is going to be on the Wednesday instead of the Tuesday, so do keep an eye out for that. So I'm getting a few questions through. How much would it cost to go to space? Well, a few years ago, there was a millionaire who wasn't an astronaut, hadn't trained to be an astronaut, and just wanted to be like a space tourist. And they paid, I think it was something like £10 million to spend a few days on the International Space Station. It's very expensive to train astronauts and get them into space, but there are lots of commercial organizations which are trying to get lower the price and get more people into space as space tourists. So for example, if Virgin Galactic ever get off the ground, they are currently charging £250,000 to spend, I think, 7 hours in space. So it's a lot of money, but it, you know, if you decide not to buy a house and to spend that money on going into space, it is doable. It is very risky, but pretty much everything is risky to a certain amount. There have been over 500 astronauts in space. There have been some fatalities. They generally happen on launch and coming back to the Earth, rather than while you're in space. While you're in space seems to be very, very safe, because there's been lots of thought that's gone into surviving well in space. Okay. How did we discover the solar system? Well, there's been different ways of discovering different things in the solar system. From the Earth's point of view, there's a lot of stuff we can see with the naked eye. So human beings have always known about the sun and the moon and some of the closer inner planets, but they didn't necessarily know what they were. And then over time, with better technology and mathematics, we could work out that there should be other planets in our solar system based on the pattern of motion, and also based on what we could see. And over time, the different planets and the outer planets and other objects in the solar system have been discovered. How many years did I study for? Well, my university degree was 4 years, and then my PhD took about 3.5, 4 years to complete. And then I also did teacher training. So I've done about 8 to 10 years of studying, not including school, to get to where I am today. Let's see what other questions there are. Is computer science a useful A-level to study physics and astrophysics at university? Yes, definitely. A lot of the work that we do now is based on computers and uses computer programming and software and stuff like that to do. So when I was doing my PhD, I was using data coming from the Cassini spacecraft, which was orbiting around Saturn. And the data was being sent back pretty quickly. And then I would get spreadsheets and spreadsheets full of numbers, and I'd use different computer programs to analyze that data. So a lot of my work was not using telescopes or visual astronomy. It was working on my computer using computer programming. So that is a very useful A-level to have. But do check with the universities that you're interested in going to and what they want for requirements for university. Let's see other other questions. So there's a question saying, could creatures live on meteorites? So meteorites are the pieces of rock that come through our atmosphere and land on the surface of the Earth. And if there was microbial life or some sort of cellular organism on the meteorite, when it comes through our atmosphere, the temperatures get really, really hot. And so it's probably likely that a meteorite would kind of get cleaned of anything that was living on it during that time. So by the time it landed on the Earth, it probably didn't have, it wouldn't, some cellular life probably wouldn't be able to withstand those kinds of temperatures. But we do know about tiny organisms called extremophiles, which can live in extreme environments. So for example, there's something called a tardigrade or a water bear, and they're tiny little organisms, and they can live in, at the bottom of the ocean, in a volcano spewing lava. They can live in space without a spacesuit and survive. So the chances of a meteorite landing with creatures of some sort on it still living could happen. I don't think, as far as we know, that that's happened so far. Can planets exist around neutron stars? So neutron stars are dying stars, dying huge stars. In fact, the first time we found exoplanets were around neutron stars called pulsars. So there are solar systems like that, but they're less interesting to humans because we are looking for planets like the Earth going around stars like the Sun, because we're looking for aliens and life like us. So we're less interested in planets around neutron stars. Question about constellations, so the patterns of stars in the sky. And the question is, what is the use of constellations? Good question. So constellations are these patterns of stars in the sky, or these areas of sky with stars in them. And they were invented by human beings, ancient Greeks and ancient Native Americans and ancient other groups of people. And they used to be used for navigation and for storytelling and for some agriculture as well. So like, for example, if you could see a particular constellation, you'd know it was time to sow some seeds. Nowadays, we don't tend to use the stars in the same way because we've got technology that does a lot of that stuff for us. But that's what constellations were originally used for. And let's see, would there be other life in space that is looking for us? Potentially, yes. In exactly the same way that we're looking for life outside of our solar system. Maybe there is intelligent life looking for us, and maybe the universe is just so big it just takes too long to get to the other side of the universe where this other life is living. Do you have to train to be an astronaut? Good question. So yes, you do. Generally, space agencies will look for people to apply to be astronauts who have already been working for 3 to 5 years in their field. So if you're a doctor, you would have been a doctor for 3 years, or if you've been an engineer, then you've been an engineer for 5 years, something like that. So you'll normally have to be about 27 as a minimum age to apply. And then you do an application, and then if you are successful, it takes about 2 years to train to be an astronaut, doing things like scuba diving, learning how to fly a plane, learning Russian, a lot of classroom work, a lot of teamwork, a lot of kind of building up resilience and creativity, and learning what to do if things went wrong, stuff like that. So about 2 years before you can then go into space. Okay, last question, I think, because we are running out of time. What's the difference between a comet and an asteroid? Well, asteroids are big chunks of rock in space, normally bigger than 1 meter diameter, but they're small enough that they're not classified to be planets. So they're too small to be planets, too big to be meteoroids, so a big chunk of rock. And they generally live between Mars and Jupiter in the asteroid belt. Comets are also big chunks but they tend to be rock and ice rather than just rock, and they tend to be found at the edge of our solar system in the Kuiper Belt and Oort cloud. So comets are kind of big dirty snowballs, big chunks of ice and rock, and asteroids tend to be similar size potentially, but generally just rock and not so much ice. Okay, so I'm going to have to finish today's session. I can see there are still some questions. If you want to email me, you're absolutely welcome to do that. I'm going to type my email address into the chat now, but also if you email the Eventbrite link, then that gets directly to me as well. So you can send me questions or ideas of topics or anything really if you want to by email. Otherwise, do keep an eye out for the link for the session in 2 weeks' time. If you've got ideas for topics, send them to me as soon as you want to, and sign up for the next ones. Hopefully you've had a good time today and you've learned something, and hopefully you are staying safe and well in this situation. And do keep in touch. If you want to give us any feedback or anything like that, do keep in touch. And it's been lovely to see you all. And I will see you again, hopefully in a couple of weeks' time. Take care, everyone. Bye-bye.